Okay, the notes for section 11.3, which deals with polar functions. So polar coordinates, points on the plane are defined by r theta, where r is the distance from the origin, O called the pole, and theta is the angle from the initial ray that you can think of as the positive x-axis. So essentially what you're looking at is some point out here, that distance is r, that angle is theta. Okay, so find rectangular coordinates for the points with the given polar coordinates. So 4 comma pi over 2, so if you don't think about that, pi over 2 rotates me up here, and then 4 is 4 units out from the center. So that point is just 0 comma 4. Mathematically, what we can do is the x value is equal to r cosine theta, and the y value is equal to r sine theta. So this would become, in this case, 4 cosine pi over 2, and this would become 4 sine pi over 2. So the cosine of pi over 2 is 0, the sine of pi over 2 is 1, so this becomes the point 0 comma 4, just like what we got before. So this one we'd have negative 3 cosine pi, and then negative 3 sine pi. So this would become, cosine of pi is negative 1, so this becomes 3, that becomes 0. So this one we'd have 16 cosine 5 pi over 6, comma 16 sine 5 pi over 6. So the cosine of 5 pi over 6 is negative root 3 over 2. So this would become negative 8 root 3. This is going to be actually just 8, because that's a half. So there we go. And the last one be, let's see here, I'm just going to write the answer down. It's going to be negative 1 comma 1. So negative 2 times the cosine of negative pi over 4, negative root 2 times the sine. Okay, find two different sets of polar coordinates for the points with the given rectangular coordinates. So this one works a little bit differently. There's two ways you can do two different sets. You can either add 360s or 2 pi's, or you can add 180 and change the sign on the r. So if you do a half circle, you flip the sign on the r. Now we can kind of so the equations we need here, r is equal to the square root of x squared plus y squared. So you think about it, it's if we have some point here, this distance is x, that distance is y, r is the hypotenuse of the right triangle. Define theta, that's the inverse tangent of y over x, opposite over adjacent. So for this one, the r value is going to be 1, and our theta is actually going to be 0. So, or I could do, another one would be 1 comma 2 pi. Or I could do, if I change by 180, I do negative 1 comma pi. So all three of those are the same place. All right, so negative 3, 3. So the r value for this one, we would do negative 3 squared plus 3 squared underneath the root. So that's root 18, which is 3 root 2. And the angle would actually be the inverse tangent of negative 3 over 3, over positive 3 over negative 3. What your calculator will tell you is negative pi over 4. But negative pi over 4 is down here. Your point here is up here, so I have to add 180 to it to get it back to where it's supposed to be. So the actual angle is, I just lost where it was. That plus 180, so plus 4 pi, so that's going to be 3 pi over 4. So I could use my negative pi over 4 if I make this negative. So I'm off by 180. I have to change the sign here. 0, negative 4, 1, 2, 3, 4. That point is down here. So that theta is root 3 over 2. The r value is just 4. So 4 comma root 3 over 2. Or we could do negative 4 comma, so off by 180. And the last one here, the r value is going to be 1 squared plus root 3 squared, which actually is 2. So 2 comma, and that angle, inverse tangent of root 3 over 1 ends up being pi over, nope, not pi over 6, pi over 3. So 2 comma pi over 3, or we can add 180, which would give us, that's 3 pi over 4 pi over 3. There you go. All right, graph all the points. So r equals 2. So what this is saying is that it does not matter what our angle is. We are always 2 units from the origin, which actually just draws a circle of radius 2. R equals -2 is actually the exact same thing, except you just start over here. Radius 2. Theta only equations are lines. Pi over 6 is about 30 degrees, so we'll call it like this. So over here, we have the side where r's are positive. Over here, we have the side where r's are negative. Because in this case, we're locked on our angle, but we can be any distance from the origin, which is why we draw a line. Okay, produce the graph of the polar curve. So this guy, so your calculator can graph in polar equations. We got sine 6 theta. So it looks like this. So this is actually a rose with 12 petals, like that. That actually should go out to a radius of 1, because that's the coefficient here. 1 minus 2 cosine theta. All right, so 1 minus 2 cosine theta. So that lovely shape there. So this one, let's see here, we got -1, -2, -3, up 1, up 1. So we got like this lovely little loop guy, then it crosses there, and then goes through -3, then comes back around. All right, 4 sine theta. Oops, not 4 cos. Is circle. It hits 0, 1, 2, 3, 4 there. So actually it's a circle centered at 0, 2 with radius 2. All right, so here's the equations we had before. This one's a little bit different because I didn't move the tangent over yet, but same thing. Use the polar rectangular conversion to show the polar graph of r equals 4 sine theta is a circle. Let's see here. So I don't have anything to do with sine. I have an r sine. So what I need to do is multiply both sides by r, which gives me this. Well, r squared is x squared plus y squared. R sine is y. So I need to bring everything to one side. Now to turn this into an equation of a circle, I need to complete the squares. So the x is nothing to worry about because there's no regular x term, but the y, in order to complete the square, you divide that value in half and square it. So 4 divided by 2 is 2, squared is 4. Now since this is an equation, if I slap a plus 4 on the left, I also have to add 4 on the right. And then we're going to factor. So this factors as x minus 2 squared. So this is the equation of a circle centered at 0, 2 with radius of the square root of this number, which is 2, which is just what we had. Okay, polar graph of r as a function of theta is the curve defined parametrically by r x equals r cos theta or f theta cos theta, y equals r sine theta or f theta sine theta. So essentially you're replacing r with your equation. So use the slope of the rose curve, or find the slope of the rose curve, 2 sine 3 theta. So our x value is r cosine theta. Our y value is r sine theta. So to find the slope, that's dy dx. So dy dx is equal to dy d theta. So the y equation, 2 sine 3 theta sine theta divided by the derivative of the x equation. Oops. Okay, and we're going to evaluate this at when theta is equal to pi over 6. Now, these, you have to work the product rule out on the top, product rule out at the bottom. Now, you do these separately. That's not a quotient rule. It's derivative at the top, whatever that is, derivative at the bottom, whatever that is. I don't want to work through all that, and then evaluate pi over 6. So if you do that, you get dy dx is equal to root 3, I believe. Negative root 3. If you do all your substitutions. Now to write the equation of line, I also need the value for x and for y. Well, here's my equation for x. So the x coordinate is going to be 2 sine pi over 2 cosine pi over 6. So if I plug pi over 6 in for my thetas, the y value is going to be 2 sine pi over 2 sine pi over 6. So the x value ends up being root 3. The y value ends up being 1. So the equation of the line y equals m, negative root 3, x minus my x value, root 3, plus my y value, 1. So there you go. Cleaning this up doesn't really make anything better because you're going to be trying to combine. Actually, well, let's see, negative root 3x plus 3 plus 1. Because when you multiply a root by itself, just the number gets. So negative root 3x plus 4. So there's your slope-intercept form. Okay, so you've got areas enclosed by polar curves. So area of the region between the origin and the curve r equals is from angle alpha to angle beta is given by this. So find the area of the region in the plane enclosed by the cardioid, r equals 2, blah, 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 blah. Okay, so we got 1/2 r squared is our formula. So from 0 to 2 pi, normally they take a full cycle. So 1/2, so if we square this, we get 2 squared is 4, 1 plus cosine theta, quantity squared, d theta. So this would be the same thing as from 0 to 2 pi of 2 times 1 plus cosine theta squared, d theta. And then we go to our calculator. Menu, so option calc, the integral of 2 quantity 1 plus cosine theta squared from 0 to 2 pi gives us 16 pi units squared. I think I typed something wrong. Did I lose the squared? No, I don't think so. Let me try something else real fast here. Make sure that number doesn't seem quite right. Oh, that's why. See my variable, if you look up here, I got a dx and I got a theta there, so that's probably not. We need to change our function type back to y equals. So let's see if this gives us a different answer. 2 quantity 1 plus cosine x squared from 0 to. Yeah, that's what I thought. So it's 6 pi. So you have to be careful. You have to make sure your variables match. You can't have this in terms of theta and that in terms of x. Otherwise, you get the wrong thing. Okay, find the area inside the smaller loop, the limmason, blah, 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 blah. Okay, so the limmason looks something like, so it starts out, if we watch the graph this, it starts here, goes around, oops, through the origin, loopity-loopity, and back out. So we need to figure out what those two values are. If you watch it trace it, the two values are 2 pi over 3, or when it goes to the origin, and 4 pi over 3. And where you set that equal to 0 essentially and solve, you get two values. So if you solve this, so when is the radius 0? Where does it go through the origin? You get this, so you get negative 1/2 equals the cosine of theta. So the inverse cosine of negative 1/2 is equal to my angle. That occurs at two places. It occurs at 2 pi over 3 and at 4 pi over 3. So when I do my integral, I'm going from 2 pi over 3 up to 4 pi over 3 of 1/2 times 2 cosine theta plus 1 squared d theta. And then calculator says 0.5 quantity 2 cosine theta plus 1 closed squared from 2 pi over 3 to 4 pi over 3. And this comes out to be about 5.44 units squared. All right, so we also do the area between two different polar curves. The area of the region between R1 and R2 is given by this lovely formula. So outside curve, inside curve, between the two angles. So R1 is the one that's, sorry, R2 is the outside curve, R1 is the inside curve. All right, which brings us to example 8. Find the area of the region that lies inside the circle R equals 1 and outside the cardioid. So circle R equals 1 is a circle of radius 1. Cardioid does something like this. And so it crosses here and here, which down here this angle is negative pi over 2, up here is positive pi over 2. So we want inside the circle, we want this area. Now we can't use pi over 2 to 3 pi over 2, because if we do that, we're looking at the area outside the circle and inside the cardioid, this side over here. So we have to be continuous. We can't go pi over 2 to 3 pi over 2 because that would have to mean we track around this way. We have to start here and end up here. So we have to start at negative pi over 2. So our formula, so from negative pi over 2, or you could go from 0 to pi over 2 and double it. It'll work the same way, which actually might be the easier way to do it. So we'll do 2, we'll put 0 there. So it's going to be 1/2 quantity R2 squared minus R1 squared d theta. So R2 is the outside, so 2 from 0 to pi over 2 of 1/2. Okay, so it's going to be then 1 squared minus 2 minus, so it look like this. So we can actually then factor this 1/2 out front, so it goes away entirely. He's going to pull a constant out. So if we work this out, this becomes 1. If I FOIL this out, I get minus 1. That would be plus 2 cosine theta minus cosine squared theta d theta. So the 1's go away. So I'm just left with this formula. And then we go to our calculator, which we could have done too, like way up here. But so 2 cosine theta minus cosine theta squared from 0 to pi over 2. And this comes out to be about 1.215 units squared. So there you go. Yeah, there's a quick review. There is actually one last sheet here. This is just a sample of polar curves. So if r is a constant, you get a circle. If r is equal to some number times sine, you get a circle that sits on the x-axis above. If you get r equals some number times cosine, you get a circle that sits to the right. Now if you make a negative, it'll flip to the bottom or left. You also have some rose curves. So you get this shape, r equals a sine n theta, where n is odd, you get the same number of petals. If n is even, you get twice the number of petals. For the cosine curve, if n is odd, you get the same number of petals. If n is even, you get twice the number of petals. So same things before. For 2n, if your coefficient on the theta is an even number, you actually have twice as many petals. You also have the limesons, limeson with an inner loop. This one is a cardioid, so here's your general formula, a plus or minus b sine or a plus or minus b cos. So if a is less than b, so the ratio is less than 1, you get an inner loop. If a is exactly equal to b, you get the cardioid shape. If it's more than 1 but less than 2, you get the dimple shape here. And if a over b is more than 2, you get this kind of flattened circle-y looking shape. Then you have the lemniscates, which look like these guys. They're infinity loops, essentially. That is the end of the section.